So thanks, George, for the invitation to present our paper on multi-stage graph problems on a global budget here. This is joint work with Klaus Heger, Anne-Sophie Himmel, Rolf Niedermeyer, Malte Renken, and André Sachenka. And my name is Frank Kammer. Okay, let me shortly introduce my notion on temporal graphs. So a graph in which the edge set can change in every time step is called a temporal graph, or shortly in every step. And during this talk, I denote with n the number of vertices and tau the maximum number of steps the temporal graph have. This is also called the lifetime. And so this is, for example, what we see here. So the graph in step 1, then step 2, 3, and so on. And the graph we have by combining all these edges, this is the underlying graph. What are multi-stage graph problems? To describe them, let me consider as a running example vertex cover. So here we have 5 graphs, and in each graph we are shown a vertex cover by the red vertices. What is a vertex cover? This is a subset of the vertices of a given graph, such that every edge has one endpoint in the vertex cover set. So here we can observe all edges have one endpoint here, here, or here. So this is a vertex cover. And here we have further vertex cover instances. And we can see here this vertex cover size is 3, here it's 2, and so on. I denote in the following the solution size with K. And what are multi-stage graph problems? Here now the goal is to find a solution in every layer. Now we consider these graphs not independently. Now we consider these now as a temporal graph, step 1, step 2, and so on, such that the difference in subsequent layers differ not too much. And often one focus on a certain bound on the difference from one step to the other. And then, for example, we say that the difference from one step to the other is we have only R different differences. This is another parameter. And here in the example, I give you now an example for multi-stage vertex cover with R equal to 1, which means we are allowed to change the solution set from here to the next step only by one vertex. And to get some intuition on the problem, one can observe some difficulties. Here, from here to here, we have 2 changes, and this is not allowed by our local budget. So what we can do, for example, we can increase the solution size. We can add another vertex, as you can see here, so that we can go from here with only one vertex changing. And what also can happen, we are forced to do some change to add a vertex from here, from the solution set to this one, absolutely unmotivated, but this helps us in some later step, so that we here have not to pay 2 changes. This is the multi-stage problem on temporal graphs, which I call in the following the classical multi-stage problem, which is considered in many other papers before, recently, but in several other papers, to name just a few of them. And as we just have seen in the previous talk, there are also further kind of multi-stage problems where the solution set and the changes are combined in some way. What we are doing is we consider a global multi-stage graph problem. Now we do not bound the change from one step to the other. We have a local, not a local parameter, we consider it globally. So we bound the total number of changes between subsequent solutions. And again, let me return to my example. Here, it's now fine that, for example, we have only 5 changes over the whole lifetime. And then it's okay to have 2 changes from step 1 to 2. Whereas where we save some something in some later step. And again, we have, for example, costs of 2. So the global multi-stage problem gives us more flexibility on the problem. To our knowledge, this kind of global multi-stage problem was considered before only by Rome in a bachelor thesis at TU Berlin, and he focused on a poly-sized kernel parameterized by k and tau, so the solution size and the lifetime. Before I present our new results, let me give some motivation on the problem. So assume we are on the construction place, and the goal is to place supply units for as cranes for the construction or containers for the employees. Here I took a photo from from Berlin Airport, where if you focus here where my mouse is, we see there in February is no container, and in March we have 1 container. Then in April we have 2 containers. In May change, and then they disappeared in June. And now if you focus on the sky, then we see several cranes, but in July more cranes, and again a change in the cranes, and so on. So such a construction place and many other problems can be easily described in a temporal graph with the constraints we have. And then the goal is to find some solutions satisfying these constraints. And if we have a local budget, this means we have a fixed amount of workers that are able to do some change from one step to the other. So it's good motivated. But we can also consider that we have a global budget, money that we can spend much money in one step to the other, where we save money at some later step. So if we have a fixed amount of budget, then it's more a global budget that we can spend to do the changes. So I think both problems, the classical and the global multi-stage problems, are well motivated. And here are now our results, which we recently published in TCS. We have found a framework that allows us to solve all these blue problems more or less in the same way, in running time that is polynomial in n and in tau, the lifetime, and some exponential function in k plus l. And I will present in a few seconds some details how we get this vertex cover result, what is our framework. And at the end of the talk, I will give you some intuition on the W1 hardness proof for vertex cover if the parameter is only k. What is interesting, also the lower bound proofs are very similar. I also want to remark that problems as ST-pass, ST-cut, or matching, where in each step we want to have a certain number of edges in the matching. We are not interested in a perfect matching or maximizing the matching. These problems are usually simple on usual graphs, but they turn to be harder than vertex cover, cluster editing, and so on. Somewhat surprisingly, I think. And since this is one of my research interests, we also focused on the working space. On all these yellow algorithms run in the number of bits the algorithm needs is only polynomial in k plus l, then k times log n, which is necessary to store a solution and some possibility to iterate over the time steps. And if we assume that k and l is a constant, then this space bound is optimal. Even if we get nice runtime, we also get a very nice space bound. And this space bound is almost parallel, in the complexity task parallel. Only this term we have to ignore. We have to find some idea to skip this term. So these are my results. And now let me come to the framework. To describe the framework, I start with some definitions. So let f be a computable function, some computable function, and k is the solution size. In the following, I will say that a graph property is enumerable with size f if the following holds. If I consider all minimal solution sets of size at most k, that satisfies the property on a given instance, then this number of solutions must be bounded by f of k. And if this is the case, then we say the graph property is enumerable with size f, if this is possible for all instances. And from this definition, now another definition, if we now fix a set f and then say we consider only the sets, the solution set, that are a superset of our given set f, and we still have the property that the number of solutions we have are bounded by f of k, then we say the graph property is superset enumerable. I also call a graph property monotone if I can take a solution, add some more elements into solutions, vertices or edges, and then this maintains the solution. Then the graph property is monotone. And finally, I call a kernel a full kernel if the kernel contains all minimal solutions of the original instance. And what I can conclude from these definitions is if I have a monotone problem and a full kernel for some graph property, then I know that this graph property is also enumerable with size 2 to the f of k, or also superset enumerable. Why is this the case? Well, because I can take the kernel, iterate over all possible subsets of size k or smaller than k, and check if it's a valid solution, and I can output it in my enumeration, and so I get an enumeration that is bounded by that size. So it's superset enumerable with size 2 to the f of k. And now, what is the framework? The framework is, if we have a graph property that is superset enumerable with size f, then we can solve the problem in the time and the space bound we already have seen. And from the previous observation, also from the previous slide, we can conclude the same also for graph properties that are monotone and have a full kernel. The space bounds slightly change. This comes from the f of k going to the 2 to the f of k, but we can also show slightly better bounds in a second framework. But this is more or less we get for free. So the interesting aspect is how can we get this framework? The main idea, the key observation is as follows. Assume we are given an instance, a graph for some graph problem. Then we can observe that this given instance has always an optimal solution in such a way that the solution Si in step I can be obtained in the following way. It is the union of a minimal solution for step I. So consider step 2. Here we know the two red vertices are a minimal solution, and the union of some vertices of the previous step. I will not go here into the details, but I really hope that this is plausible. The minimal solution to take is nice, and it might be useful to take some more vertices, even if they are not required here, because they help for later instance. So this is a very short intuition on it. And if we now have the key observation, we can come to our algorithm, which works as follows. We iterate over all steps of the temporal graph from 1 to the lifetime, from I equal to 1 to the lifetime. And in each step, we check if the solution of the previous step is still valid. And if this is the case, then we simply take this solution. If this is not the case, which can happen L times, which is our global budget, then we number all minimal solutions. For example, here in step 2, in particular, we find also these minimal solution consisting of the two red vertices and decide, we guess, which vertices we take over from the previous step. And this number of vertices is also bounded by a function in k. So what we have to do is, these guesses means we iterate of some f of k possibilities. So the algorithm here above, what is the runtime and the space bounds? L times we have to do these guesses. guess which minimal solution you have to take and which of the vertices are take over, but this is bounded by some function f of k. And what do we have to store? To do the iteration, we have to store which guesses we already have done to do the next guess and the next guess. So we have to store the initial guess, so the initial solution, and the L guesses, which means we have to store k plus L such numbers of size f of k, and some numbers to do some verification in the graph of size O of n, and to iterate over all the lifetime. So we also need to store a number of size O of tau. And from this observation now, we very simply come to our runtime. We do the verification and iterate over all graphs, and then we do the guessing L times from some number f of k. And the space bound also is very simple. If you store that many numbers of size f of k, then we have this space bound here to store a solution and to iterate over the different time steps. So this is our framework very shortly. And now I want to focus on the lower bound. Again, vertex cover is a running example for the reduction to show that vertex cover is W1 hard if the parameter is only k. We make a reduction to click, which is also W hard. So we are given a click instance and we construct now an instance for the global multi-stage vertex cover. So we construct a temporal graph. But what we do is, for every vertex in the click instance, we take a set of vertices, capital 1, capital 2, that corresponds to the vertex in the click instance. Even if I draw such a vertex only on the left side, these vertices, all vertices appear in every layer, but I draw in the layer only the vertices that are of interest. And then for each edge in the click instance, we have several layers. What is interesting is we have some special vertex, and if it's the edge, for example, 1, 3, then we have here a vertex, a special vertex W star, which connects to all vertices in capital V1 and capital 3. And what we now can observe is, if we have a click solution, then assume we take exactly the vertices in the click solution, then the corresponding capital I sets. And if we now allow the solution size of a size that these are exactly the vertices that we are taking due to the click solution, and we have one vertex for free, then we jump with this vertex over all these vertices here, exactly if this vertex is not taken. Or here in the special rule, and this is the interesting aspect, if now this edge is part of a click, then these vertices are already part of the solution set, these vertices are part of the solution set, so we can save the jumping to this vertex. And how many jumpings can we save? If we have a click, then we can save exactly k tilde over 2 edges. This is exactly the numbers a click has. So if we allow relocations for this one jumping vertex exactly in such a way that we must save all the vertices, all the edges in the click, and all others are okay, then we get the correspondence between the click instance is solvable exactly if the temporal graph is solvable. So this is the idea of our reduction, and all these other layers we have here, they are only to guarantee that it makes no sense to choose some other vertices here. It is only the best thing you can do is in fact choose the vertices of one set capital I and then other, but not to mix something in between. So this is the proof. And what is interesting is that our other W hardness proofs are very similar. They are also reductions to a click instance and then some adaptions. Let me conclude the talk with some open problems. As we can see, here are some question marks. So how can we solve how is a problem W hard, or can we solve it in polynomial time? For the parameter k plus tau, there are some question marks. What is if you take other parameters as the tree width or the tree width plus something else? How can we solve the weighted versions of the graph instances here? And how can we solve problems that are not enumerables, that are not monotone? And can we modify the algorithm above to run in parallel? Thanks.